All right, so we've talked about color theory. Red, green, and blue are the primary receptors we have, right? That's the colors we detect, so we use those as the primary basis for our color system. You can make other color systems using other colors as primary colors, but this is what we use because it's what we have receptors for, okay? So the cones in our eyes largely respond to blue light, red light, or green light. So those are our primary colors. When we have all three colors being activated, we perceive it as white. So white light isn't a color of light, it's all three primary colors mixed together. If you just have red and green, your brain perceives yellow. If you just have green and blue, your brain perceives cyan. So this is kind of an easy one to remember. Green and blue is like the color of the sea, right? Sea is cyan. Just kind of helps me to remember. And then red and blue are magenta, okay? So the idea here is that if you have all three colors, green, red, and blue, what would happen if I somehow was able to remove the blue light? What would be left? If I had red, green, and blue, and I removed the blue, what would be left? Carson?
Yellow.
Yeah, you'd have red and green left, which you would perceive as yellow. So we can think of yellow as white light from which the blue has been removed. Does that make sense? So if we had a chemical, a pigment, or a dye that removed blue light from white light, what color would it look?
Yellow.
It looked yellow. So yellow is what we call a primary pigment, okay? So yellow, magenta, and cyan are our primary pigments. They are the chemicals which remove one of our primary colors. So you don't need to write this all down because it's all in that table and we're going to practice using it. But this is the same table except color-coded. Our primary colors, all the colors together make white. The absence of all light is black. So technically black is not a color, it's the absence of light. Red and green make yellow, red and blue make magenta, and blue and green make cyan. But when we talk about pigments or chemicals that selectively remove colors, we have what we call pigments, and yellow is the pigment that absorbs blue. So if I shine white light, and the blue is removed, you will see red and green, which is yellow. Magenta is the pigment which absorbs green. And you can get that from your table, because if you look at the table you just made in your toolbox, right? What is opposite green? Magenta. See how magenta is opposite green? They're complementary. And cyan absorbs red light. So, fun fact, if you were a lobster and you wanted to hide and not be seen on the bottom of the ocean, what color would you be? What colors are lobsters?
Red.
How is red a good color for somebody that wants to hide? Well, it turns out that water, by and large, absorbs red light. So if water absorbs red light, what color does water look to you when you're underwater? Blue-green. If all the colors of light from the sun hit the water and the red gets absorbed, what gets to the bottom of the ocean? Blue and green, which is cyan, which is why blue-green is the color of the ocean, right? Now, is there any red light down there? No. So if you were a lobster, what colors do you reflect? Red. But there isn't any red light down there. So lobsters in the ocean actually look black. You don't see them because no red light gets down there. So they're not bright red in the bottom of the ocean. There's no red light down there. So it's okay to be red because there's no red light down there to illuminate you. All right, so if we have all the pigments together, we absorb all the light, and that's what we call black, okay? All right, so here is some conceptual questions that I just want to kind of quickly practice, all right? So using your diagram there, think about this. We have cyan and magenta pigments that are mixed together on a paper. So think about what does cyan, so we're going to shine white light on the paper. What does cyan remove? Alex? It removes red. What does magenta remove? Green. So if we have white light and we remove the red and we remove the green, what's left? Blue. So it'll look blue. Okay? So on your color printer, when you want to make a blue letter, the computer puts down cyan and magenta pigments. So that when you shine white light on your page, the red and the green are absorbed by the chemicals, and all that's left is the blue. Okay? Does that make sense? Okay, try another one. If you're sitting next to somebody, see if you can convince them. A blue light shines on a yellow dress on the stage. What color will you see? If blue light shines on a yellow dress. So a yellow dress means it has a pigment. And if it looks yellow, what does it absorb? Blue. So if we shine a blue light on something that absorbs blue, what's going to be reflected? We're just shining blue light on it.
Black.
Nothing will be reflected, which we perceive as black, right? So this is the art of stagecraft. You can dress somebody in different color clothes, and you can change the spotlight so they're all blue, and the girl in the red and the yellow dress disappears. She just turns black. You can't see her back there next to the black curtain. It's kind of wild. So the answer is black. Last one. Cyan light. Okay, now this is light. This is not a pigment. Cyan light. So what colors are in cyan light? Blue and green. We got blue and green light. It's passing through a yellow filter. What does yellow absorb? Blue. So what's left? Green. Does that make sense? So you'll see a couple conceptual questions about color theory that kind of look like this. I'm just asking if you can sort of understand the difference between colors and pigments, right? Cyan light is made of is made of blue and green light. But a cyan pigment is a chemical that removes red, okay? All right, so we're gonna move on. We're gonna talk about optical phenomenon, and this finishes up the unit. So first thing we're gonna talk about, skip that, is mirrors and lenses. So you guys have solved a bunch of problems involving lenses. And I've got a little simulator that shows how that works. So I just want to quickly show you how this works. We've been doing lenses. And instead of a pencil, I'm going to use an arrow, and I'm going to use the primary rays. So this should look like what we've been doing. Okay? We have an object right here. The light leaves the object, gets bent by the lens, and forms an image. As the object gets farther and farther and farther away, the image gets closer and closer to the focal point. That's what we did in lab last week. And as the object gets closer and closer and closer to the focal point, look at the image. It's getting farther away and bigger, right? So that was 10.5. We solved problems like that. 10.6, we asked what happens if the object is closer to the focal point. It's closer to the lens than the focal point. And in that case, these rays of light diverged, and we traced them back with dotted lines to see where they seem to be coming from, and that was a virtual image, right? So that was 10.6. We solved problems like that. And to make the virtual image bigger and bigger and bigger, you got to move the object closer and closer and closer to the focal point. But if the object is closer than the focal point, if the object is in here, you get a virtual image. And if the object is over here, you get a real image. All right, that was the idea that we did. Now, we have other kinds of lenses. We have what are called diverging lenses. These lenses bend light outwards. So instead of causing the light to bend towards the focal point, they bend the light away from the focal point. So light coming parallel gets bent away from the opposite focal point. Light that's heading towards the opposite focal point gets bent parallel, and light that goes through the middle is not bent. So it's the same kind of three rules. We are not going to solve problems with this, but if you were solving problems with this, the cool thing is it uses the exact same equations you've been working with. 1 over F equals 1 over dO plus 1 over DI. Those equations describe all of the relationships here too. But you always get a virtual image, and you guys actually have a lens in your box. So look in your box for the lens that says 15 centimeter double convex. See the one that says 15 centimeters? No, double concave. If you hold that up and look at anything, close or far away, like look at me through it. Does it look like there's a little me in there? It's a virtual image. The light is getting bent, so it looks like it's coming from a little Blatchley instead of a big Blatchley or medium-sized Blatchley, right? And if you have glasses, you might notice that, hey, that kind of looks like when I look through my glasses. Because glasses are diverging lenses. They're thinner in the middle and thicker on the edge. We primarily use diverging lenses. They don't form images. They don't form real images. Everything they make is virtual. We primarily use them for correcting vision or for correcting light that's been bent too much. So that's a diverging lens. Kind of fun. Now, there are other ways to form images. We've been using lenses to bend the light together to a focal point. But you can also bend light together using a mirror. A curved mirror causes the light that hits it to come to a point also, right? And you can use mirrors to form images. So that looks like this. So if I switch to mirrors down here, I can go back to my arrow like I normally did. Here we go. So here is an arrow, like a candle, and light is leaving it. Instead of being refracted or bent towards the focal point, it's reflected to a focal point, and it keeps going. And one of them goes through the middle, and one of them goes this way, and they all end up over here. They form an image over here. And so you can form images just like we did lenses. You can do it with mirrors. Now, I bet most of you have a concave mirror at home that you use in some form or another, okay? Here's an example of how that might work. If we put the object closer to the focal point, where's the image? It's over here. Is it bigger or smaller than the object? It's bigger, it's magnified, right? So if you have a makeup mirror at home, it's a curved mirror. You use your face as the object, you put it closer than the focal point, and then you see an image in the mirror that is magnified. All right? So you can try that on this one. Hold it pretty close and pull it away slowly, and something really scary will happen. All right? Just try not to get fingerprints all over it, and don't drop it. You can also hold it at arm's length and look at things. Like I can look at the clock right now. It's on the wall over there. I can see an image of the clock in here, and it's upside down, which is exactly what happens if you hold one of the converging lenses at arm's length and look at the clock. It's small and upside down, right? It's a virtual image. So, take a look at this. So start with it close, and then pull it a little farther away. And if you want to try this at home, you can use a spoon. Now, there's another one that you're used to, guys. I bet you have a mirror that looks like this. It's a mirror, and we are using the convex side of it to produce virtual images. So I have an object here, the light gets reflected, and it produces an image right here. Where might you have this kind of mirror? Besides the back of your spoon. Anybody have one of these? It usually has a warning on it. Objects in mirror are closer than they appear. Whereabouts on your car? Yeah, your right-hand side view mirror is actually curved. So you can see a wider field of view, but when you see a person in there, they're smaller than they would normally be if the mirror was flat. Because it's a virtual image from a curved mirror. And so that's why the warning is watch out, right? The object is closer than it appears. It appears that this tiny little person is really far away because they're tiny, but really they're right behind your car. But because of the curved mirror, their virtual image is smaller. So we use mirrors to produce images also, okay? So we're not gonna do this. If you took a course in college, you might study in more depth all of these different ways of producing images. The cool thing is the same equations work for mirrors and lenses, converging and diverging. Okay? So that's an app you can play with later if you want to. I just wanted to show it to you to connect with what we've been doing. All right? All right, so quick summary. When we have converging lenses, if the distance to the focal length is always positive. If the distance to the object is greater than the focal length, we get a real image, and the distance to the image is positive. That was like all the problems in 10.5. If the distance to the object is less than the focal length, we get virtual images, and the distance to the image is negative. Okay? And if you were solving a problem with a diverging lens, which we're not doing, but if you were, the only change you would make is that f is negative. And because f is negative, every image is virtual. You cannot get a real image from a diverging lens. Okay? All right, so that's kind of the summary of the images. Now, we can put optical elements together and make compound optical instruments like a telescope. So try this. On your track, put the 10 centimeter lens at like 5 centimeters or something, and put the 20 centimeter lens at like 35, so that they are 30 centimeters between them. So make sure the 10 is close to the edge, and the 20 is 30 centimeters away. So you're going to make yourself a simple little telescope here. Now, if you've got the 10 here and the 20 centimeter lens there, the 10 centimeter lens is your eyepiece, you can hold your telescope up and whoa, Jackson. You can look at things. They are magnified in your telescope. There's Alex back there. Notice what the image is. It's reversed. Look at the clock.
I'm gonna go look at my telescope again.
That would really be a shame.
Oh no.
All right, so you can make a telescope. Now, we have little tiny lenses. They're not very impressive.
Oh no.
Your telescope only has a magnification of 2.
It's blurry.
You're blurry.
Okay.
So here's what's going on in a telescope. You can't see, use your telescope. We have an object that is far away. We wish to make the object look a little bigger. So we have a lens. We call this the objective lens. That's the 20 centimeter one on your set, right? So our setup, back up. Our setup is kind of like this, okay? Back up. Here's the objective. It's the first one. If I'm looking at something far away, like Drew. Oh, hi Drew.
Hi.
Here's an object far away. This first lens produces a real image of Drew right about here, okay? Near the focal point. It's small, but it's here. This image right here is a real image. The light rays actually converge there. So once they get here, they spread out again, and they spread out into the next lens. So this object, this image becomes the object for the second lens. And since it's closer than the focal point, the second lens produces a virtual image of that image. So we use one lens to produce an image, and the image becomes the object for the second lens. And here is the virtual image I see of Drew over there. So we can stack together lenses in clever ways to make optical instruments. So a telescope's an example of one. What's another example of an optical instrument we use with multiple lenses?
Microscope.
A microscope, yeah, and it works in a very similar principle, except the object you're looking at is not far away. Now, telescopes have a problem. This telescope over here is a 700 millimeter telescope, and I can use it to look at things like Jupiter. So last week, Jupiter's in the western sky after sunset, and so we can point this at Jupiter, and we can see the moons going around Jupiter. It's kind of cool. but it is a refracting telescope. It's got a big lens in front, and that bends the light. The focal length is pretty long. It's from here to here. It's a 700 millimeter telescope. So the focal length is 70 centimeters, okay? And that produces an image for my eyepiece, which is the second lens, which produces a virtual image, and I can see the moon or Jupiter or whatever. But when I look at distant stars that are supposed to be circles of light, they actually look like this. They are blurry. And this is a problem with all refracting optical instruments. Do you remember what dispersion is? What's dispersion? Who's got it? What's dispersion? Tell me what dispersion was.
Isn't it like the distance between the red light and violet light?
Yeah, it's the spreading out of the colors because they bend slightly different amounts, right? So if I have white light, here's kind of a picture of what's going on. I have white light coming into my lens. The blue light gets bent a little more than the red light, which means the blue light, the green light, and the red light do not focus at the same point. It is impossible to get all the colors to focus at the same point with refraction because the colors spread out a little bit because they have slightly different indices of refraction. They slow down different amounts. Now that's what caused the rainbow. That was cool. Rainbows are cool, but not when you're trying to find out what's going on with a star. It's all blurry. So this is a problem inherent to all optical instruments that use refraction. So we need a better telescope. Any ideas? Who do you think invented a better telescope? Hint, what's the answer always in physics? When we say who?
Newton.
It was Newton. Yep. Newton's the guy that discovered that white light is actually all the colors mixed together, and he also was the one who was able to propose a better way to build a telescope that didn't have this problem. Now, this problem is called chromatic aberration. So chromo means of color, right? Like chromochrome, where else would we use chromo? Chromodynamics? No, let's see. Chromo means color. I can't think of any other examples. And aberration means screwed up, right? So it's when colors are screwed up because of refraction. So Newton solved the problem by making a telescope that did not use refraction. He used a mirror, which uses reflection. And for reflection, all the colors reflect at exactly the same angle. And so he could build a better telescope using a reflecting objective instead of a refracting. So a refracting telescope that bends light, like you guys made, right? We call that a Galilean telescope because they were used primarily by Galileo initially to look at the heavens. We call a telescope that uses a mirror a reflecting telescope or a Newtonian telescope. So Newton, reflect. Galileo, refract. Okay? Galileo has problems. Galilean telescopes have problems because of chromatic aberration. The colors bend different amounts, you get blurriness. All right, so microscope is another example of an optical instrument. If you're curious and you want to delve into how that all works, it's kind of cool, but I'm going to move on. All right, let's talk about another optical effect for a minute, a mirage. So a mirage is what you see when you're driving on the road and it's hot. And along a streak of road, it looks like there's water on the road. Have you ever seen one of these? Maybe you were hiking in the desert and you were really thirsty and you saw an oasis over there and you hiked towards it and you got there and it wasn't water at all. It was a mirage and then you died. Happened to anybody lately? No, probably not. That's why you're still here. So, what is going on right here? Well, the question is, why do you think there's water there? You can't see water, right? Water's clear. But what is it about water that would make you think there's some water there?
The ripples.
The ripples, or maybe the reflection is what makes you think there's water there, right? I mean, what you're seeing here is a reflection of the trees there. And then here you kind of see the reflection of the trees and a reflection of the road. It looks like there's something shiny there reflecting the light. And in our experience, what is usually on roads that's shiny that reflects light? Water. So you think there's water there, but there's not. What's happening is that there's nothing there reflecting light. What's happening is there is a very hot layer of air right above the pavement. So the pavement gets really hot in the sun. And when it's hot, it heats the air above it. Sound or light moves faster in hot air than it does in cold air. So remember our old wagon wheel? Here comes some light from the sky. The part of the light down here speeds up, and it actually causes the entire wave to turn and go back up. The wave turns and goes back up. So the light that gets to this guy's eye is the light that came from the sky. It's blue, but it comes from the direction of the road. So it looks like the reflection here is reflecting the blue sky. Or, in the case of this picture, the green trees, right? It looks like the light here is reflecting. The light is coming from the trees, but it is not reflecting off of water. It's just getting near the road and curving and going back. So you see what looks like a reflection, but it's actually refraction. Okay, that's a mirage. And the cool thing is the mirage happens anytime you have a really hot layer near a colder layer. So the air can cause the light to change directions. That happens in reverse in a couple of special circumstances. So in the pirate lore, there's these stories about floating ghost ships, right? They weren't just completely smashed and drunk. They probably did see them sometimes. And here's why. It's the exact same thing as a mirage, but in reverse. If you have really cold water and warm air above it, then light leaving a boat heads this direction, but in the warmer air it moves faster than the colder air near the water, and so it curves a little bit. So it gets to your eye over here, but it comes from this direction. So you think the boat is, the light is coming from this direction, the boat is up there. And so you can see a floating ghost ship. Now it's not really a ghost ship, it's just a regular old ship. And it's not floating, it's just a mirage. But it looks like it. So yeah, it's pretty cool. So this happens oftentimes when there's warm air near cold water. So the North Atlantic off the coast of Ireland, places like that where the water is really cold, but on a hot summer day the air can be warmer, you see this effect. So it's kind of cool. That's another example of refraction. Now, another example of refraction is light going through our atmosphere. So our atmosphere is not homogeneous. There are pockets of warm air and pockets of cold air. And as light passes through them, it gets refracted a little bit this way and that way and that way. I mean, you can see me because there's not a whole lot of air between us. But if you're looking at something really, really, really far off on the horizon, have you ever noticed it kind of shimmers and dances a little bit? That's because the light getting to you from far away is getting refracted and sometimes it's bending a little bit. Light from a star directly overhead goes straight through the atmosphere and it gets refracted and bent a little bit. Light coming from the side gets refracted a lot though because it's going through a really long section of atmosphere. So next time you're out at night and you see the stars, try this. Look straight up. Those stars are pretty bright and they're pretty constant. They're always on. But if you look at a star on the horizon, it'll kind of flick off and on. It'll twinkle. And that's because the light from it is sometimes getting bent away from your eye and sometimes to your eye. So it seems to turn off and turn on. And this is much more noticeable for stars that are low on the horizon than stars overhead. But no matter what you do, if you're going to look at stars from Earth, that light has got to pass through the atmosphere, and so it will refract in random ways. And that's a problem if you're trying to build a telescope to look at the stars, right? So where do you want to put your telescopes? In space. Well, let's say you can't get to space yet. It's 1910. What's the best you can do? Find a really tall mountain. And it'd be really nice if it was a really tall mountain somewhere really dark. So, for us, that's Mauna Kea in Hawaii. Mauna Kea is a huge volcanic mountain. It's dormant, and it's super high, and it's not, it's in the middle of the Pacific. It's really dark. The air is very stable. So there are 13 telescopes up there. Our best telescopes are all in Mauna Kea, and there's a mountain down in Chile in the southern hemisphere. It's also very high and on the western edge of the continents, so it's pretty stable. So that's good, but even better, of course, is to get them out in space. So we have a telescope in space. It's called the Hubble. We launched it 30 years ago. We thought it would last 5 or 10 years. 30 years later, it's still chugging along. What you see as a dot in the night sky, it sees as a Crab nebulae. So we can study all kinds of cool physics and astronomy with our telescopes. That's the Hubble. However, the Hubble is only the size of a school bus. The primary mirror that collects the light, it's this big. So it's about as big as a person going like this. We just launched a new one 2 years ago called the James Webb Space Telescope. And this is its primary mirror. It collects a lot more light. It's huge. But we had to launch it on a rocket, so we had to have it fold up. Not only is that collecting area really big, but it's got a sun shield that's the size of a tennis court. And all of this had to fold up inside of a little rocket capsule. We launched it to space, and then it had to unfold. So for 3 months, like every scientist in the world held their breath, hoping every part would work as this thing unfolded. And it did, and now it works. And now we're getting some amazing pictures. This is what Hubble sees. So this is called the Pillars of Creation. It's a feature in the night sky and a distant nebulae. It's a star formation region, and those are pillars of dust. And that's what Hubble can see. This is what James Webb can see, because it uses different wavelengths and it's got better resolution. It can see all, what you just see there is a hunk of dust. It can see as lots and lots of stars forming in a region with different temperatures and stuff. So it's pretty cool. So our telescopes are optical instruments, and they work best when we get them out of the Earth's atmosphere up in space. Okay? All right. New topic, different topic. If we went outside, and if we come back from lunch and have time, we'll go outside and try this if you want. If you hold your hand in the sunlight, let's say the sun is coming down, and I hold my hand here, will you see a shadow of my hand on the table?
Yeah.
You will. And could you tell how many fingers I'm holding out from my shadow?
Yeah.
You could. But if I go to the top of the stadium and I hold my hand out and you look at the shadow all the way down there on the ground, it'll be really fuzzy. Why does the shadow get fuzzy? Well, it's because of an effect called diffraction. Diffraction is when waves hit a barrier, and then after the barrier they spread out. So imagine you had ocean waves coming in towards the harbor, and you had a big seawall with a little break in it. Some waves would get through that break, right? But as they get through the break, once they're through the break, those waves start to spread out again. So it's not like you're just going to have a column of waves the rest of the way through the harbor. The waves will spread out. If the gap is wider, they'll still spread out. And if you only block them on one side, they'll still spread out. So when you block sunlight with your hand, it produces a sharp shadow close to it, but far away, the waves, the light, as it goes around the corner of your hand, start to spread out again. And it'll get really fuzzy on the edges. And that's called diffraction. And we use that for some important science investigations, but I'm not going to worry about that. We can look at actually crystals and shine light through them and look at the diffraction that's produced and understand the structure of atoms. It's called diffraction spectroscopy. Okay, last thing. Almost done here, guys. Hang in there. I'm going to give you some special lenses here that you can play with. So I think there's enough for everybody to get a set. Please do not scratch them. Don't set them on the table and then drag them across the table and lift them up. Take them out. There's 2 in each bag. So we'll play with them for a second, and then we'll try to figure out what the heck's going on. So here's what you can do. If you have 2 of them, you can hold them up and you can look through them. When you look through them, the world looks a little darker. Yeah? So like Polaroid sunglasses. If you put them together, you can still see through them. But here's where it gets weird, guys. Watch this. If I put them together and then I rotate one, watch what happens. So it's completely black if I rotate them, but if I have them the same direction, light goes through it. So these are called polarizing filters. okay? Try this. Look at my TV through one of them and start to rotate it. It'll go black at some angle. I'm not sure I can show this on a video or not. Let's see. If I hold one up in front of the video and I rotate it, it goes black. Hey, it worked! And if I hold two up, you can see through them, and if I turn them perpendicular, it blocks the light. So, what is going on here? Well, let's try to explain what's going on here. Here's the idea. Light is a wave, and it wiggles. The electric field wiggles in every direction. So if I have light from up here, all of the atoms that are vibrating to create that light, they're all creating light wiggling in different directions. So some of the light is coming this way, and some of the light is wiggling this way. What a polarizing filter does is it acts like a gate. It doesn't allow light to get through if it's wiggling the wrong direction. Think of it as jail cell. So if I had a jail cell, I had bars going up and down, I could wiggle a spring up and down in the direction of the bars, right? And that wiggle would get through. But I couldn't wiggle a string through bars that are going opposite the direction I'm wiggling it, right? So what happens with light is that only the light, if my gates are going up and down here, only the part of the waves that are going up and down can get through. The waves that are going side to side get blocked. Which is why when you take your polarizing filter and you look at a light, it looks a little darker. It's blocking some of the light. But here's the thing. The light that does get through, it's all wiggling in the same direction. So if you hold a second one up, it doesn't make it any darker because everything that got through this one is already wiggling side to side, and so it goes through the second one. But if I turn it perpendicular, all the light that got through the first one is now blocked by the second one, and it goes completely black when I rotate it, okay? So that is a polarizing filter. So light that is wiggling every direction gets blocked by one filter, so now it's only wiggling up and down. The second one's perpendicular, so it doesn't let it get through, okay? So how do we use this? Well, first of all, have you heard of polarizing sunglasses? Yeah, people wear sunglasses made out of this thing. Why would you do that? It's pretty expensive. You could just get tinted sunglasses for cheaper. Well, here's why. Light, when it reflects off of non-conducting surfaces like water or sand or the road or snow, the light that is reflected is polarized on reflection for complicated physical reasons. But the point is, the light that is reflected off the water or the road or the glass in the car in front of you is polarized. It's all wiggling side to side to side. So if you have sunglasses that have gates going up and down, it will block all of the glare. Not just some of it. It doesn't just make it darker. It blocks the light that is polarized. So here's some examples. Here's a picture. Look at that one. Can you see the glare in the picture from the sun? It's hard to see. It's a bad picture, right? We put a polarizing lens on the front of the camera, and you can take a picture like that. Okay? It just blocks all of the glare. Now you can see the bridge, nice and clear. Here's another example, looking at a car. Here's a better one. Here are 3 pictures of a car window. This is what a car looks like on a sunny day, right? You've seen that. If you wear tinted sunglasses, it makes the whole scene a little darker. It looks like this. But there's still a strong reflection of light from the clouds. See the clouds here? Now, that reflected light is polarized. So if you wear polarizing sunglasses, it completely blocks all of that reflection, and the picture looks like this. So this is tinted sunglasses, this is polarized sunglasses. Because there is no glare anymore, you can actually see into the car. So police officers wear polarizing sunglasses because it allows them on sunny days to see into your window, right? In the old days, pilots used to wear polarizing sunglasses because if you're flying an airplane, there might be a glare off the runway or off the water. if you go skiing, if you work outside a lot where there's a lot of glare, polarizing sunglasses don't just make everything a little darker. They actually completely remove all reflected light, all glares. Okay? Now, pilots used to wear them, but there's a bit of a problem. Nowadays, our electronics uses polarized light to produce screens. So take your little polarizing lens and look at your computer screen. Turn your computer on, look at it through this thing and rotate it. At some angle, your computer screen will go black. You just need one. Look at your Apple Watch. Look at your calculator. Look at my TV. It doesn't matter. Does the iPad screen do it? Does it go black?
Not entirely, no.
But close?
Yeah.
All of these devices are using polarized light. That's why a polarizing lens blocks it at some angle. If your calculator is the old kind, like Alex, yours, turn your calculator on and rotate the filter in front of it, it'll go completely black.
This one, like, it's the opposite. So, like, when you can see through this and see this.
It's the opposite of my screen?
Yeah, so, like,
Yeah.
if you have it like this. You can
Yeah.
see it.
So here's kind of what's going on, guys. We have a special little cell. It's called a liquid crystal display. You heard of LCD? Liquid crystal display. What it is a special little cell, and if we apply a voltage to it, it causes the liquid to line up like a crystal. And that produces polarized light. And so, the light that gets through it is the light that is polarized. And so, you can produce displays, and you can change the voltage on this millions of times a second. So you can turn these off and on very, very fast. And they act as our little display units. So whether you're an iPad, a watch, a calculator, a TV, they're all made up of these little tiny cells that cause the light coming out of them to be polarized. And that's why the polarizing lens can block it at the right angle. You may have noticed in your car that a lot of your electronic displays have the same effect. If you were to take your polarizing sunglasses and rotate them, everything on the dashboard would go black because it's the wrong angle. So nowadays, most of the time, the LCD controls on your car are polarized at a diagonal angle, so you can still see them with your sunglasses on. But when they first did it, they didn't think about that. You put your sunglasses on and you couldn't see how fast you were going, or your oil temperature, or anything on the newer cars that had liquid crystal displays. And that's why on some of the newer computers, I think if you have the new computer, it goes black at a 45-degree angle, not up or down. So that's polarization, okay? All right, so here's a quick concept summary before we head to lunch. These are the things I want you to know. Reflection of a wave happens when it bounces off a boundary. Refraction is when the wave bends as it passes into another media. Refraction happens with light, like we've talked about that, but it also happens with sound, and it happens with any wave. It happens with ocean waves. So anytime the wave changes speed, it changes direction. Dispersion is the spreading out of the different colors because they all refract at slightly different angles. And dispersion is how we get the rainbow, the colors spread out. Diffraction is the spreading out of a wave after it encounters a barrier. So the shadow of your hand gets fuzzy. That's diffraction. And polarization is when light is filtered so that all of the electric waves are oscillating in the same direction. So there's a lot of terms floating around in this unit, okay? That's just a quick summary of the main ones. All right, so you should probably have a good working understanding of that or have them in your toolbox. It's up to you. So I'm gonna stop here. I'll leave that up there. We go to lunch in like 7 minutes. If it's sunny after lunch and you want to, we can go outside and play with the lenses. That's the end of the unit. So to finish up, I've got some review assignments for you. I'm not gonna be here for you guys on Friday. I'm going to Purdue because Purdue's graduation is Friday morning for the School of Health and Science, which is what my son is graduating from. But you're just gonna be reviewing for the test. I've got a concepts review, I've got a problems review, and I have bonus problems. And if you want to, you can get working on those now. If you finish 10.6, you're welcome to work on that. Okay? So that kind of wraps up the unit. Okay, that's it. Put those things back in the little plastic bag, please, if you